Question 13 wants us first of all to estimate delta H for this reaction given the data on there. So the key to that is to remember that this is the equation that relates delta G to the temperature. So this is the equation that defines what the graph looks like. And the important thing is that when T is 0, in other words, along this line here, when temperature is at absolute 0, if T is 0, then T delta S is 0. So therefore delta G is just equal to delta H. Okay, so this means that delta G is equal to delta H when T equals 0, because that term just vanishes. So we can just read off what delta G is when T is 0, and the answer is plus 20 kilojoules per mole. So we can therefore say, so delta H is equal to plus 20 kilojoules per mole. Make sure you put the explicit plus sign in there, it's not just 20, remember it's plus 20. And then it wants us to estimate the entropy change. So there are different ways that you could do that. You could in principle choose any temperature and figure it out, but the easiest one is at this temperature where delta G is 0. So we can say at 400 Kelvin delta G is equal to 0. That's what the graph tells us. So delta G is equal to delta H minus T delta S is equal to 0, which means that delta H must equal T delta S, so that when you subtract the two you get nothing. And so we can find out what delta S is just by rearranging that equation, that delta H divided by T is equal to delta S. And delta H we've just worked out is plus 20. So plus 20 divided by 400 is going to be our answer, which is plus 0.05. And that will be kilojoules per Kelvin per mole, because the delta H was in kilojoules, so the entropy that we get out will be in kilojoules. And that would do fine as the answer, but if you wanted to turn it into the more normal units of joules per Kelvin per mole, you just multiply by 1000, okay, which is equal to 50.0, so plus 50.0 joules per Kelvin per mole. Okay. Part C wants us to comment over the range of temperatures over which the reaction is feasible, and you can see that that's basically above here, because at all temperatures up to 400 K delta G is positive, which means it's not feasible, but at temperatures above it becomes feasible. So this is typical endothermic reaction behaviour where it only becomes feasible above a temperature. So the answer is that it's feasible at all temperatures up above 400 K. And finally we get this sort of observation that we've been using these sort of very simple looking graphs where you get these straight lines here, but often they're actually curved. And you can see the reason for this is that this straight line comes from us kind of in effect assuming that delta H and delta S are both independent of the temperature. But in real life they're not. And as soon as those become additional variables, then that won't be a straight line anymore. So that's the answer. It's because in real life delta H and delta S are not constants, they are themselves functions of temperature. But for simple reactions, the straight line is often a reasonable approximation.